Okay, so in the last Friday, in the last Friday's lecture, we focusing on the how to using those pressure depth relations, right? How the pressure is variation with depth, especially for the manometer, for different type of manometers. And also at the end, we're starting to introducing that how to calculate overall resultant pressure force if there is a flat plate is submerged in a static fluid. Okay, and we talk about that. You'll be seeing that if you have flat plate, submerged in a fluid, so there will be parallel pressure forces working on this plate. And because the direction of these forces is always the inverse normal direction of the surface, because the pressure force is always, in the inverse normal direction of the surface normal direction. Okay, and all these parallel pressure surfaces, what we want to do is that we try to reduce it to a single resultant pressure, right? Resultant pressure force, a single one. And we need to calculate. We do not need to care. We do not care about the direction, because that since all this parallel direction for this flat plate is all toward to the inward of this plate normal direction. So what we only need to know is two things. The first thing is that what the magnitude of this force resultant force Fr will be. And the second thing is that we want to know that the point of application of this force. In other term, which is also called the center of the pressure. Okay, and in the last class, we quickly go over that how the magnitude of this pressure force is calculated, right? And so this is how this how we calculate the resultant, the magnitude of this resultant pressure force F over R. And to calculate it is pretty simple. Okay, it's just like because we know that pressure is a stress, right? Is a force per area. So all we need to do is that we just integrate this pressure overall the whole surface area. Okay, and since pressure is can be given with this pressure depth relationship. The P0 is atmosphere pressure, and this H is depth below the surface of the fluid. And especially for this problem, which is a flat plate submerged in this inside this fluid, is not straight. Okay, it's with an angle theta. So this depth basically is given by this correlationship of y equal to sin theta, whereas the xy coordinate is defined is in this picture. The y is along this plate direction. Okay, so simply substitute this both pressure and this depth expression into this integration on pressure over the area. Okay, we put it inside, and because P0 rho g is constant, and so the only thing left is all this P0 is the atmosphere times A is this big A is the area of this plate, flat plate, surface area, and this rho g is constant, sin theta is constant. So the only thing left is this integration of y times dA. And we know that if you took your statics class or mechanics class before, okay, so we know that this y of dA is the first moment of the area, right? And also that the centroid, okay, the centroid of this surface, y of c, basically is given by a of integration y of dA. So in the other words, so this integral here can be represented by y of c, which is the y coordinate of the centroid, times the surface area. So we can do that replacement here. So the problem, and substitute this one into this equation here, and the magnitude of the resultant pressure force will become, a simpler form, which can be written in this form. And this h of c is basically y times c times this sin theta. So this h of c basically is if this is the central, right? So this HC is the depth. So assume that this is central. So this is H of C basically is the depth this of this at this central location. Okay, and in this way, okay, you can see that this P0 is the atmosphere pressure, and this rho G HC, which is the gauge pressure at this point location of C, right? Because it's give you rho G and times this depth. So this rho G times HC is the gauge pressure. Gauge pressure plus this 1 atmosphere pressure P0. So all we get is that all we get is that you can write this just as a single P of C, which this PC can be this P of C is equal to this P0 plus rho G of HC, and this P of C is called the absolute pressure in the liquid, okay, which is at the location of the centroid of the plate. This C means centroid. So what this telling us? It's telling us that if we want to calculate the magnitude of the resultant pressure force, okay, all we need to do is that 2 steps. The first step is that to try to find what this H of C will be, right? To find that what's the centroid of this plate, and what the depth at this central point will be under the water, under the liquid, and then we can simply using this P0 plus rho GHC to calculate the absolute pressure at this point, the centroid point of this plate, okay, and simply times this PC with this surface area, so we can get the magnitude of this resultant pressure force. Okay, so this is the cases, this is the results, and it's pretty simple one, the final results. So if there is another, so this is the cases that it's only valid that if when we assume that there is no pressure force on the other side. Okay, when in these cases when we calculate it, we are only thinking that the pressure force on this side, on the left side. Okay, we on the right hand side, on the right side of the plate, we didn't assume any pressure there. Okay, but if the problem, okay, like this, if this is the water gate of the dam, okay. And if there is on the right hand side, it also has a P0 pressure here on the right hand side. Okay, so all we need to do is that we can simply using the left so calculate this F or R. Okay, by assuming that it's just like if you have the P0 on the right hand side, so the left hand side pressure it just be reduced by this P0 one because they cancel each other. So the net pressure force, okay, will be given the overall, pressure, resultant pressure. And in that cases, okay, this is simply, you can replace this PC with P gauge, PC of gauge. What is this PC gauge? PC of gauge is equal to P of C minus P of 0. Okay, so if you need to consider, this atmospheric pressure at the right hand side, so you need to convert this equation a little bit, change this PC to the P gauge, because the reason is that on the right hand side you also has a P0 pressure force, and you need to cancel it from the left hand side. So that and this PC minus P0, the absolute pressure at the centroid minus the 1 atmospheric pressure, basically you get that the gauge pressure, okay, at the centroid location. And what this will be just equal to this rho GHC, okay, rho GH of C. Okay, basically you do not have this P0 anymore. So this is the gauge pressure. Okay, so this is how we to calculate the magnitude. Okay, remember that this is only give you the magnitude of this resultant pressure force. Okay, and also we also know that the direction of this pressure force is always normal to the direction of this flat plate and also toward the inside. Okay, and the next task, okay, is try to find that this point of location. So will this pressure force is working on this point or on this point or on this point or simply working on the centroid? Can we do that? Okay, so that is our next task. So any question here, guys? So this is basically, I just quickly review of what we doing at the end of the class, last class. Any question here? So just simply knowing that if you want to use the equation, you need to find the centroid first, and then using centroid to know that at that centroid point what the pressure will be. And after you have pressure times area, you can simply get the resultant pressure force magnitude.
So everything up until now, we were finding the resulting force, and now today you're going to show us how to find the centroid point, and then from there we can determine the pressure.
Today we need to. So the next the task is that to find this so-called center of the pressure. So where is this point of application of this force will be? Center of pressure. Okay, and I can tell you that this is not equal to centroid. Okay, I can tell you the conclusion first is that do not think that this FR can be just thinking that they are working on the centroid. No, okay, it's not. I will show you later. Okay, so we need to find that if we reduce all this pressure force, parallel pressure force, to a single resultant pressure force F of R, and there how we can find this point of application will be for this force.
Would the center of pressure equal the centroid if there was an even distribution of forces?
Yeah, it will be, if this is the pressure force is evenly distributed, it will be equal. Okay, but it's not. Okay, you see that this is
right. It's at an angle.
So actually, you can already get a conclusion that this center of the pressure actually will be a little bit lower than the center of the centroid, because that the lower this area will be, the larger the pressure loss will be. Okay, so, and we will calculate that. And before we do that, okay, we just have I want to have a very quick math review of all this concept of so-called centroid, first the moment of area, second moment of area. Okay, so that we can, on the same page when we later on we use this concept. You should already be get familiar with this in your statics mechanics class or statics class. Okay, and so let's using the most simple area shape. Okay, let's assume that this is a rectangular, or you can see the flat plate with rectangular shape. Okay, let's first consider the first case. Okay, where we put our XY axis origin at the center. Okay, let's assume that we simply put this center of this XY axis at the center of this flat plate. Okay, so how we calculate the centroid of it? So the centroid, basically, this is the first moment on X. This is the first moment on Y. So you just divide the first moment by total area. So you can get what's the coordinate for the X coordinate for the centroid and what's the Y coordinate for the centroid. Okay, you simply do this integration here. And this dA here, because now you are integration on the X direction. Okay, so you can write the dA can be just equal to this overall height times the small delta x, right? So that will be x times dhx. And do this integration, and remember that the coordinate from f of x is from minus b over 2 to the positive b over 2. So you do this integration, you will get x equal to 0. And similarly, you can also do this for the y coordinate of the centroid. You will also get it 0. So what this means? This means is that the centroid for this rectangular flat plate will be just will be just located at the center of the plate. Okay, so because it's both x, y is equal to 0, right? And now let's calculate this x is called this I is called the second moment of area. Okay, so you have two indices below, right? X and x. So this means that how you calculate this moment regarding to which axis. So that means that I want to calculate this moment, second moment, regarding to x-axis and x-axis. So that's what is the distance to this x-axis will be y. So distance to x-axis, distance to x-axis. So you have 2y. So that's why we have y squared here. Okay, you integrate on y squared or dA, and you simply do this. Okay, and remember that for y is starting from the minus h over 2 and positive until to positive h2 over 2. This simple integration will give you the result will be b times h to the h cube over 12. Okay, b is the width on x direction, and h cube h is the height on the y direction. Okay, so this give you the so-called the second moment, okay, of area regarding to the x-axis. And similarly, you can calculate the second moment of area regarding to the y-axis. Okay, so y is that regarding distance to y, and we know that the distance to y-axis is x, right? So that's why you have to do x squared over dA. All right, and you do this integration, and x is from minus b over 2 to the positive b over 2. So this is will be the result. So you see that this result is very close, but the only difference is that it's h and b, and this cubic power, is one is on h and one is on b. And the last one, okay, is called the mixed second order moment. Okay, so this is one for x and one for y. One for x will be y. Okay, one for y will be x. That is the distance to this two axes times dA. So you do this integration, okay, you find that the result will be 0. Okay, why? Because that because both x and y, they are odd equation, odd function in itself. So if you integrated them, separately on this minus b over 2, positive b over 2 minus h over 2, positive h over 2, they will cancel. Okay, the positive part will cancel with the negative part. So your result will be 0. Okay, so all this is a pretty simple one. Okay, and now let's thinking about that. If we change this center, okay, let's try to define this xy axis not at the center, not put the origin at the center, at the centroid point. Let's try to put this xy at the corner. Okay, like this bottom left corner, the origin point O is located at the bottom left corner of this plate. What do you get? We just can continually to do all the same calculation. Everything is the same, but the only difference is that this when you do integration, this lower bound and upper bound, this range will be different. Remember before is that if you locate at the center, right? The origin point is at the center. We are from minus b over 2 to the positive b over 2, minus h over 2 to the positive h2. But now it's from 0 to b and 0 to h instead. And you will get a new result. Okay, so for the x location, for the centroid, get b over 2, and the y location for the centroid, get h over 2. And b over 2 and h over 2 in this coordinate, it will be still this center point. So basically the center point is still the same one. Okay, even that the only difference that we translate the coordinate system, to some kind of distance. And regarding to the second moment, x of iy, okay, you got this new value here. Before you get 12, now you get 3. Before you get this bh over 3 over 12, now you get bh cubic and over 3. And for this mixed moment I of xy, okay, before is 0, because you get 0 here, but now you get a new value, non-zero value, b squared h squared over 4. So why we show this? Basically, this telling us that all this moment of area, right? Their value will be affected by where you define this axis, right? So for example, this x-axis is like you want to define by the distance to x-axis different to x-axis, right? So if you put your x-axis at the bottom and your x-axis as the across this centroid point, result will be different. Okay, for this first and second order moment. So there is a theorem for that, which is called the parallel axis theorem. What does this mean? That means is that assume that we have a surface, we have this area, okay, A here, and assume that this x is the axis like across the centroid, and assume that there is another axis is x prime, which is not across the centroid, and you will have this correlation here. Okay, so this x-axis second order moment you calculated based on this x prime can be equal to I of xx, which is the second order x-axis moment, across the centroid plus area A, so the overall area of this surface, times d squared. And what d is basically the perpendicular distance between x and x prime. So by this way, actually, I can calculate the arbitrary, this second order moment regarding to, any, axis horizontally to, parallel to x, okay? And so that's why with this correlation shape, okay. So basically so basically by tradition, okay, what we really want to use, okay, is we try to use this value, okay, when we're talking about that second order of moment, okay, of area, second moment of area. We usually just try to calculate across regarding the axis regarding to the axis across the centroid, because that we can using this correlation equation and easily convert it that if the axis is not on the centroid, we can using this equation to do this kind of conversion. Okay, this is for x, and similarly you can also do this similar thing for y. Okay, I of y prime prime will be equal to I of yy, plus a of d squared. Okay, this d will become like a, this is the y prime and this is y prime. So this maybe is the d distance. You can also do this kind of thing. Okay. And so this is basically this is just some fundamental math. Okay, we want to remind you. And any question here?
We're going to see these in like examples or practice problems?
No,
like
we do not use this as example because this is not the content of this class. So I just want to remind you. All right. So because it will be used, these correlations we will use them to derive some expression later on. Okay.
Oh, okay. So we're not, because like in statics we had to derive them and stuff like that. We're not going to have to do that, right?
But you may need it for some example problem. As I told you, right? Yeah. Like example problem, like when you try to calculate that resultant force, right? Definitely you need to know how to calculate the XC and YC, right? For arbitrary, for some kind of shape, shapes, right?
Right.
Yeah. Okay. So with all these math things, in your mind, so let's continue. Okay. Now we try to find that, what this center of the pressure will be. We know the magnitude, FR. Now we want to know that what is this location of this FR will be at this point. Okay, so how we determine the point of application? And from this from our solid statics, we know that the point of application is determined by the moment balance, right? So basically, if we have a parallel pressure force working on this area, and so this parallel for each parallel pressure force, each individual one, and we need to calculate the moment of it across regarding to an arbitrary point. Now let's just choosing an O point, okay? And then this force times this distance will be the moment, and this distance will be the y coordinate of this point, right? Because we define this y coordinate on this along this plane direction. So by this way, we just simply integrate this y, the y coordinate, and times pressure, and integrate this one for all the area. So basically, we can get all the overall moment. Okay, the overall force of moment for all these parallel pressure force regarding to this origin point, right? No problem. And now, if we also want to find that this point of application of this FR, this resultant force. So we know that this force times this distance here, let's assume that is as this distance from this point here to this origin point is y prime. So we can know that this y prime times this magnitude of the resultant pressure force should be equal to, when you do the integration for all individual pressure elements on the pressure force, on the whole area at that moment. Okay, so this correlation, this moment balance, okay, single force moment will be equal to that system parallel forces moment, okay. So this one will give us that the application point on y direction, okay, the y prime value, okay, for the for this resultant pressure force. Okay, so with this equation in mind, so we just do the integration. Okay, and the same thing as before when you try to calculate FR, we put this pressure P will be is equal to P0 plus rho gh, and H will be equal to Y sin theta, right? H equal to Y sin theta. So this will be the result here. And you integrate this value and put all the constant value outside of the integral. Okay, so what do we get here? So what this term will be? So this is the first moment of the area, right? So we know that this is YC times A, right? YC times A will be equal to this one. And this one, what is what? So this is I of XX. This is the second moment of the area regarding to X and X axis, right? IXX. And remember the things, okay? This integral here, Y square. So this IXX, so it's regarding to this Y distance, right? This Y distance is defined that the origin point is on O here, okay? So basically it means that this so this IXX we calculated is basically defined on this axis, okay? Some axis, you know, not across the centroid of the area. So we need to using this parallel axis theorem and try to convert this Ix prime to the real Ix, which is that if this you know, x-axis is across the centroid, okay. So we simply assume that, you know, try to convert this so assume that this is Ix we calculate from here based on the origin point of this coordinate. So it is based on this axis here, right? So this x, if x-axis is you know, is in the perpendicular, it's a screen direction, okay? So that will be the x direction, and so this is the moment is on regarding to that x-axis. Now we want to move that x-axis to the centroid of this location in the here, okay? With this you know, parallel axiom theorem, so we can calculate this new ix, this x with the height on the top, okay? X height, and this x height is basically the second moment of area, okay, about the centroid axis. Okay, so by doing this way, so basically we can convert this one, this correlation with this one here, okay. So basically to do that, okay, we just substitute this one into here, okay, because this is ix. So we can get further. We can get, so this is what we substitute into it, into, and so by doing that one, so we can further, you know, try to, you know, rearrange it, and so we have area here, we have YC here, we have YC here, area here. So we try to, you know, combine the one with this area and YC. So we will get this one with this point here, and also we have a term for this Ix height. This is you know, second moment of area about the x-axis across the centroid. Okay, so this will be x prime, and so after we write this, so this YC times sin theta is HC, okay, because that YC times sin is basically HC. So this is again is the PC, okay. So again, this is P of C. This is the you know, the absolute pressure at the centroid, okay. And so this PC times A will give us FR, right? Resultant force. Right? Remember that this is what our result we got, right? FR equal to PC times A. Okay, so this term times A will give our resultant force, and we still have this correlation here. And now we can calculate what the Y prime will be. So you know, for the the Y coordinate for the point application, that center of the pressure for this FR, okay, it will be just equal to this one divided by FR on the both sides, will be equal to YC, which is the centroid Y coordinate of the centroid, plus this is rho g sin theta I x height times F of R. Divided by F of R. Okay, and also we know that this we have two terms here, right? And the second term basically is the difference between this Y location of the center of the pressure regarding to the centroid of this plate, right? And so this is the difference, and this is a larger positive value, which means that you know, this f of r is always below the center of the centroid of this plate. Okay, and the next step, basically, we can try to, so if we can know this I of x hat, we can calculate, you know, what the y prime will be, right? So, for example, if this plate is a rectangular plate, if this is a rectangular plate, and then we know that this will be I of x hat, y, because this is where we define this x and y x-axis across the centroid, right? So it will be 12 bh cubed divided by 12 for this rectangular plate. So you can, if you want to calculate that one, you can simply substitute this one. If your plate is a rectangular flat plate, okay, into this one here, you can quickly calculate what the y prime will be. Okay, so this gives you the y direction, okay, prime, and this is similar to what when we derive the magnitude of the resultant force. Okay, this is remember. So if you're looking at the derivation, all this derivation process, especially for the pressure term, you see that when we have this pressure term, is will including our derivation including this P0. Okay, so which means that we are using the absolute pressure. Okay, try to derive this center of application, and similar to here to these cases. Okay, if we for this plate, okay, the other side is also have 1 atmospheric pressure, and what we interested is the net pressure force. Then, you know, similar to the case here, you know, where we change this is PC to the PC gauge, okay. And if we have the same ambient pressure acting on the other side, so all we need to do is that you know, we can simply, when we do calculate this, do this calculation, okay, and we can so we can simply, you know, change doing this derivation, we change this PC to the PC gauge, remove all this P0 point, okay, and especially for this correlation, because that you know, the resistance force, because now we need to derive this by this divided by this resistance force, right? This resistance force is the PC gauge times A, and PC gauge is equal to rho G HC, right? In these cases, and so this rho G can be cancelled, and HC can be YC times sin theta, so sin theta can be cancelled. So this equation can be further simplified in this form. So remember, so this is only valid, okay, when you have P0 on the other side, okay. So this is only this equation is only used that when you have that on the other side of the plate, you have 1 atmosphere pressure, and this is working that you know, this is only valid when you do not have that 1 atmospheric pressure on the other side of the plate. Okay, so let's quickly go through this how we calculate this y prime, right? So which is the y coordinate of this center of the pressure. So but the physics behind this is that we just want to make a guarantee that the moment, okay, around the origin point is the same, for either a single resultant force or for this parallel pressure forces. Okay, and when we do this, you know, during the derivation, you know, we have 2 integral terms regarding to area. So one is for the first moment and one is second moment. For first moment, it can be related to the, you know, the centroid coordinates. For the second one, and we need to using this parallel axis theorem, so to convert this axis, you know, moment axis, okay, from the, you know, xy coordinate to the central, you know, to the central coordinate, which means that that axis has to go across the centroid. Why? Because that you know, because that all these results we get here from the literature is usually, based on this when the axis across the centroid. Okay, and with all this result we have, we put it into it, and we get two correlations. One is for the cases that when the other side of the plate do not have a P0, and this is the cases that when the other side of the plate has the P0. Okay. Any question here? So far so good. Okay. So this is the y direction of the central y coordinate of the center of the pressure, right? So similarly, we need to calculate what the x prime will be, right? The x coordinate of the center of the pressure. So similarly, okay, we also do the for x prime. Okay, x prime is the x coordinate for this center of the pressure, which is application point for that force of F of R. Okay. So we also do this moment balance. Okay, x prime times FR will be equal to x times this pressure integration over the whole surface area. Okay, and we substitute this P with this pressure depth relationship, and H will be y sin theta, and the resulting here we get two integral term here. So this is the first moment of area on x. So this is that mix the second moment mix that moment. Okay, on moment of area x of y. Okay, and similar things. Okay, this x equal to this one will be equal to xc times a. Okay, the central times area. And for this one, xy of dA, we're also using the always using this parallel axis theorem, so that we can convert both x and y axis to the axis across the centroid. So that with this relationship, I of xy will be equal to I of x hat y hat, and this x hat y hat represents that this mixed moment regarding to the xy to the x direction axis y direction across the centroid, and plus this area surface area times the xc x coordinate of the centroid point times yc. Okay, substitute this one into this integral here. Okay, so just put it inside, and just try to rearrange the terms, and we know that the P0 plus rho GHC basically is the FR. Okay, go back to FR, and this equation divided by FR on the both sides, we can calculate the x prime value. So x prime will be equal to x of c plus this rho g sin theta I of xy hat divided by F of R. This F of R is the magnitude of the resultant pressure force. And this is the cases that when the other side of the plate do not have that 1 atmospheric pressure. And if the other side also have 1 atmospheric pressure, so this correlation can be given reduced to this form. Okay, so by this way, okay, we can find that both this x prime value and y prime value, right? So now we can find, now we are able to find what is the point application of this FR resultant form. Okay, and also you can see that we find this center of the pressure. Okay, where is it located? So using this correlation. So in overall, okay, all this correlation here we derive to calculate y prime, and also correlation we derive by all this correlation we derive to calculate x prime. It's showing us that we have two ways to calculate y prime and x prime. Okay, if you want to calculate y prime, you can just starting from this equation. You can just starting from this equation, then you can calculate what y prime will be. Or you can just using this one or this one. Okay. Similarly, okay, for calculate x prime, you can just also starting from this equation, and then you do integration yourself. And all you can also using these two equations to calculate it. Okay, either way can give you the same result. Okay. Any question here? No question? Okay, so no question. We just go to example problem so that try to use this correlation we derived before. Okay, how to calculate the magnitude of FR and how to calculate this location of the center of the pressure. Okay, and please read this problem first. Oh, by the way, we will have at the end of the class we will have today's attendance quiz. Okay, so do not leave in the middle. Okay, so for this problem, we have a inclined surface here. Okay, and for this inclined surface, we know the length, we know the length is 4 meters. We also know the angle is 30 degrees, and also we know that they are with this 2 meter right depth starting. This starting point is already 2 meters below the this surface of this fluid. Okay, so the question is that how to calculate the resultant force Fr. Okay, and both the magnitude and this center of the pressure location will be. Okay, so first let's calculate the magnitude, right? How will we calculate magnitude? Remember the magnitude simply is calculated by Fr times equal to integration of this P over dA, right? So we have two ways to calculate this force pressure resultant force. For the magnitude of the pressure force, we can either calculate it using this one, or we can basically calculate it from this one directly. Okay, so which way is better? Which way? Both are okay. Okay. So let's first using the first way. Okay, simply we try to calculate this pressure force directly from this integral itself, and simply we put this P0 plus rho GH into this P, and over the dA we can try to calculate it, right? And H. So what's the any location point here? Okay, this length H will be equal to this D plus. Okay, so first we need to draw our. First we need to define our coordinate system. Okay, so let's try to define our coordinate like the y is starting from this location. So simply means that you extend this line here, horizontal line. You also extend this inclined line. So when they have this cross section point, okay, point of cross sectional point. So we define this is as the origin point. So this will be y axis. Okay, and also we know that we also can define a new axis, the eta. Okay, which eta is the same direction with y coordinate, but starting there's when eta equal to 0, that means that it's starting from this top edge of this plate. Okay, let's try to define a new one eta here. Okay, so when we calculate for any point, okay, location point here, h here, okay, and this length, so this length is eta, and then we can see that this h will be this eta times this sin 30 degree, this length, and plus this d, right? So eta h will be d plus eta plus sin 30. Okay, and the surface area here will be, you assume that this plate, okay, on the x direction the width is w, so which is a constant equal to 5 meters. Okay, so this is a rectangular plate, so all this plate is rectangular, and the width, okay, in this perpendicular screen direction is 5 meters. So the area, okay, across this this dA along this dy d eta direction. So basically dA will be w times d eta. Okay, you put this two, put this h into this pressure correlation, and put this dA to here and p to inside, so we can quickly calculate what the resultant force will be. Okay, so this will give you resultant force, and now we, instead of integrating on the dy, we try to integrate on eta, and eta is just the translated coordinate for y. Okay, eta will be from 0 to to this L. Okay, so you to integrate this eta from 0 to L. Okay, with all this correlation here, and your result after do this integration, we find that the magnitude of this resultant pressure force is this value. Okay, 588 kilonewton. Okay, so this is the pressure force. And now we want to find that what is the point of application of this force, right? So let's try. We need to find either x prime and y prime. Okay, and inside of try to calculate y prime because we define a new coordinate eta. So we try to find the eta prime on this eta coordinate. The difference is only this this is a fixed length here. Okay. So to calculate the eta prime, which is the y direction coordinate of this center of the pressure, so we can basically using this starting from this moment balance, right? From this moment balance, y prime times this fr will be equal to integration of this eta times p times dA. Okay, so we can use this one to calculate this eta prime value, which is on this y direction what this point of application will be. And on x direction, x prime, we can also using this moment balance, x prime times fr will be equal to integration on xp times dA. Okay, so let's do each one. So for y direction, eta direction, okay, we know the fr value already, so this fr value is known, and this p is also replaced with this value here, d plus eta plus sin 30 degree times rho g. Okay, and so you put this direction here, and make sure we also know that this is dA equal to w times d eta. So this is dA here, and bring everything inside, and do this integral on the eta, and so final result for the eta prime, okay, will be this value, 2.22 meters. So which means that starting from here, you go 2.22 meter, you will find that where's the location of this on this y direction location will be. And if you want to change this eta prime to the y prime, you simply need to add this additional length here, right? Additional length here, and this additional length basically is this 2 meter, divided by sin theta is 30 degree, right? So you can also change this eta prime to the y prime, so you can find similarly what the y prime value will be. Okay, so this by this way you find this y coordinate of this center of the pressure. And similar things you can find this x coordinate. Okay, what the x coordinate for the center point of for this center of the pressure point will be. So you're using this correlation here, this one, to make the moment balance, and you simply bring this fr is the magnitude of this resultant force is known, and p is p again as this this value rho g d plus eta sin 30 degree. Okay, and you put the things inside the integration, and similarly this dA, okay, is this and this dA, because now you integrate on x, and x dA will be w times dx. Okay, so in this case is dA will be w times dx. So you just do this, so you get the final result. You get 2.5 meter. Okay, and so this is one way you can find both this fr, x prime, and y prime. Okay, you remember that now we didn't using all those concepts of xc, yc, ixx, ixy, right? We didn't using all this in the centroid coordinate and this second moment of the error. We didn't using this concept at all. We just strictly starting from the basic theory that the resultant force will be just integration of pressure on the area. And if you want to find y direction, x direction, this point of the center of the pressure, you simply make the moment is balanced. We're just starting from here, try to derive everything. So this is the first method Okay, and there is also a second method which I want to using this xc, yc, ix, ixy values. Why? Because that we know that this is a rectangular plate, and for this rectangular plate, I already know all these values will be. I already know all this value is given, right? Xc will be 0, Yc will be 0 if this is on the center of this application point, and Ix, Xy if it is on the center, you know, we know this value here, and it's even for Xy, we know it's 0. Okay, and so there is also the second way to solve this problem, which is using this algebraic equation here. For the f of r, the magnitude of the pressure force, now we try to not starting from this equation. Now we try to starting from this equation. So what this equation means, it means that we need to calculate PC first, right? So we need to know what the YC will be. After we know YC, we can calculate HC. We can get this PC here. Okay, and so for this one, the second method, so FR will be equal to PC times A, and so it will be rho G H of this is typo on the textbook actually. So it's H of C, okay. Rho G HC of A, and this HC is equal to basically the YC, right? And what is YC will be? We know that for the flat plate, this centroid form will be just in the middle, right? In the center. So this will be, so this from here to here will be L over 2, right? This distance will be L over 2. And so by this way, we know that this HC will be D plus L over 2 times sin 30 degrees. So this gives you our HC and the plus this D. So this is will be, so that value is that how this H will be, right? This H will be. So this is, you know, L over 2 times this sin 30 degree and plus this D. So now we know that this is H of C. And by doing this way, we can quickly calculate what the FR value will be. And using this equation, okay, put all the parameters that you have, you will get the same result of this FR value here. Okay, and similarly, when you want to calculate the y prime and x prime, now we can try to using this equation, okay, this equation and this equation here, using this moment of area and this xc value, yc value. Okay, so similarly, okay, if you want to calculate y of prime, you calculate I of x hat of a of yc, and this I of x hat will be equal to this will be equal to 1 over 12 WL cube, because we already given, right, in our previous one, because it's a rectangular plate, it will give this value, because that is the one when you're at the center, right? So your coordinate defined center. And so by this way, we already know that value. You provide this x, so all this parameter here into this equation, you can quickly calculate the 0.6 what y prime will be. So you will also get the same result as this y prime you get here. And similarly for x prime is now you need to using this correlation and using I of xy. And remember, I of xy at the center will be equal to what? Equal to 0, right? Remember that we mentioned that if it's a rectangular plate, so this will get 0 here. And so this makes the calculation even simpler. So if you can calculate what the x prime will be. Sorry, what the x prime will be simply equal to xc. So on x direction, x prime is simply equal to xc, you can get 2.5 meters. So now I show you that there's two ways to calculate this FR, this x prime, this y prime value, right? One way is that you can directly starting from this basic physics theory behind, right? The pressure force is this resulting force is pressure over area, and x prime and y prime is determined by this moment balance. Then you do integration yourself, or you can also using this derived result we get here for both FR and xy, x prime, y prime, and using that those centroid location xc, yc, second moment xy, ix, xy, you can quickly calculate it. you will get the same result. Both methods give you the result. And also for this problem, you do realize that, you know, for the method 1, when we calculate pressure, P, right, we directly assume that equal to, you know, P0 plus rho GH, right? Now you have P0 here. So this actually, our textbook, okay, this nice addition really has a lot of things that really makes people confusing, and also some typo here. So this P0 is basically neglected. Okay, so basically in this problem, we try to work in the gauge pressure. Okay, so although he writes the P0 here, but basically he assuming that there is another P0 on the other side. Okay, on the other side of the plate. That's why is that later on when you see these correlations, for the second method, we're using this correlation, and we're using this correlation here, and we're also using this correlation here. All this correlation is the cases that we're using this one actually, but we should assume that on the other side of the plate we also have 1 atmospheric pressure. Okay, and we also for that example we're using this equation. We didn't use this one, and for the FR, you know, similarly we try to using this one, not using this one. Okay. So when you go through this example problem, be careful about that. Okay. Okay, so this is a important example problem, right? Basically, it gives you a very good exercise that how to calculate this resultant pressure force, both magnitude and you know, pound of this pressure. Okay, center of the pressure. Any question here, guys? No? Okay, so if no question, let's go to another example problem. Okay, so for this problem, okay, so we have a tank here, okay, a water tank, okay. So we fill with water, okay, all this water here, and we assume that we have a door here, okay, and the hinge of the door is at this location here, okay. So that to stop this water flowing out, to stop this door is opened by this fluid pressure, water pressure, on the top of this wall, right? We need to put a force, this F of this is T or L, F of T here. Okay. And the question is that what this force should be to stop it. Okay, because this is the hinge, okay. So obviously this is a moment balance problem, right? So this force F of T, you know, regarding to this hinge axis, this moment should be equal to the pressure force regarding the moment of the pressure force regarding to this hinge, right? That is the problem, how we can solve it, right? So when we write this free body diagram, okay, so this is that door, and this is the hinge. Okay, so this force here, F of T requires the force we are asking for, we want to calculate it, times this distance L, which is this length of this door, should be equal to this pressure force, resultant pressure force, times this distance, right? This distance. So this distance is determined by this center of the pressure, where this FR, okay, where this pound application will be. So it go back to our first problem, right? We need to calculate both the magnitude of this FR and also this pound application Y prime with this value. After we get Y prime, so FR times Y prime should be equal to L times this FT. By that way, we can calculate FT, okay? And first, we calculate F of R, okay? And so F of R can be equal to PC of A. So here, I think we use the second method. from this centroid method, centroid moment area method. What is peak of C? Peak of C is absolute pressure at the centroid of this gate, right? This gate is a flat plate, okay? It's in rectangular shape. So we know that the centroid basically is in the middle, right? We know that the centroid is just here in the middle because it's a rectangular flat plate. And so we calculated P will be P0 plus rho G of HC, and HC will simply of L over 2, okay? And this gamma is rho G, okay? Is specific weight. So, and also times area of this plate will be just B times L. And so by this way, we can calculate what the resultant force FR will be. And also we want to calculate what is Y prime will be, right? What this Y location will be. This Y prime location will be. And it will be equal to using this correlation we have here. This correlation here, okay? So Y prime equals YC rho G sin theta XX divided by FR. So YC plus rho G sin theta, theta now is 90 degree, okay? And the times IXX divided by FR, and IXX equal to letter B times L Q, this B times L cubic divided by 12 is this IXX. When we talked about it earlier, when we're talking about this second moment of area. And divided by this FR is given by here. Okay, so this by this way calculate Y prime. And now we do this moment balance here to calculate this FT, because that this FT times L should be equal to this FR times this L divided by Y prime. This is Y prime, so this is L. So L divided by Y prime, it will be this distance here. Okay, and by doing this way, okay, this moment balance, so we can quickly calculate the what this FT value will be, and substitute this FR Y prime correlations from these two, and bring all the numbers. You can calculate what the final result will be. Okay, the final result is 600 pound force. All right, so this example problem is also very straightforward. Okay, and it's the same thing, right? We find what the magnitude of FR. We find that what the Y prime value will be, and then we just do a moment balance and try to find the force we want to calculate it. So, any question about this example problem? Anyone? No? Okay. So here, we spend like almost a whole class, right? Try to go through that for a flat plate, if it's submerged into water or liquid, okay, what the resultant pressure force will be, and also where this center of the pressure, okay, this point of application for this resultant pressure force can be calculated with all this derivation we have, okay. And remember that in the beginning we talk about that when we're talking about this submerged body, right? So basically we are focusing on two types, right? Now we finish the first one on a flat surface, and the next one is for the surface is not a flat plate, it's a curved surface. And what's the difference between these two? The difference is that on the flat plates, right, all the pressure force they are parallel, which means that this pressure force, their direction is same. They are all normal, and they are all in the inverse normal direction of this surface, right? And because this normal direction of this surface is not changed, so this pressure force is also not changed. And on this curved surfaces, then the story will be different. So at each point now, at each local point on this surface, okay, we know that the pressure force will also be normal, will also be in the reverse normal direction of the surface at this point. but because because the normal direction of this surface is also keep changing. The normal direction here is direction at this point is here, and the normal direction at this point will be here, right? So the normal direction of this surface is also changing. So the pressure, the direction of the pressure will also be keep changing, right? So you can see it here. And so what this makes the thing difficult? So it makes things like this is if you're looking at the flat plate cases, so this is simply similar like a 1D problem, right? Because everything is on one direction. But for this one, things become 2D, okay? When you consider the force, because all this, the pressure force is just one direction. All the pressure force is only on this positive x direction. On this one, your pressure force, can be either on x direction or on y direction or be combination of them. Okay, so your pressure force will become 2D problem. And for this for this 2D problem, okay, the way we can represent this pressure is that instead of using scalar in this flat plate cases, for this curved plate cases, we are going to using the vector to represent the pressure force. Because that you can see the pressure force, their direction has both component on x direction and has a component on the y direction. So basically, we can write it in these cases when we're talking about pressure, we are talking about P equal to P of x times I plus P of y times G. So this is the way we are going to use, okay, to handling this, curved submerged surfaces. And so I will just give you a start for this topic. Okay, I do not think I can finish this topic in this class. So we just let's have a small start for it. Okay, so let's assume that we have this curved surface here, okay, and this area dA, and remember looking at this A here, I add an arrow on the top, which means that this area element is also a vector. Okay, and what's the vector direction will be the normal direction of this dA element area. Okay, and if you for this so by doing this, okay, we can define that the pressure force, the element pressure force on this element area can be calculated by dF will be equal to minus P. P is the pressure at this point here times D of A. Okay, and we have a minus sign here. Why? Because that we know that your pressure force is always be the inverse direction of your area normal direction. Because pressure force is always going inside. Pressure force is always try to squeeze your fluid. Okay, and squeeze the atom submerged into the fluid. And that's why we have this minus sign here. Okay, and so with this correlation in our mind, right? So if we want to calculate the overall, resultant pressure, F of R, which is also a vector, okay, we can try to integrate, this element pressure force overall over the whole surface area, okay, integrate this P times dA over the A. If we can calculate this, we can calculate what the FR will be. Okay, but usually, okay, we didn't do this way, okay, because that is not easy to directly integrate a vector, a vector over a surface. So what we did, basically we try to write this vector both for the force and area in the component form. Okay, for the force, we try to write this force, okay, into 3 components. The resultant pressure force in x direction component, in y direction component, and in the z direction component. So by this way, we write the pressure force will be I times FR over x, I G times FR over y, and K times FR over z. This IJK is the unit vector on XYZ direction. Okay, so by this way, we write this FR into this component form. And similarly, for this area A, okay, we can also try to write it into 3 component form. So we can write this dA as this dAx plus times this I direction normal, and plus dAy times j normal. This j will be this direction, and plus this dAz times k vector, this k vector here. So if we can write this dA, this area vector into this 3, and what this 3 means? This 3 simply means that for this dAx, basically is this area, this surface area. If you do a projection of this area on this YZ plane, what this projection area will be? This will give you AX. For AY will be this area, the area you do a projection on this XZ coordinate, what this area, surface area will be. Similarly, for this AZ will be this, the area you do a projection on this XY plane, what this projected area will be. Okay, so by this way, we can also write this, area vector, into 3 components. So, what's the correlation shape between this FR and each component of FR and each component of this area? So you can get it from this correlation here. Simply, FR of X basically is the overall vector form, their projection on the I direction. You do this one, you do put this change FR equal to this one, and you put what the DF will be PDA, and this dot is not the multiply. Okay, this dot is the scalar product between the 2 vectors. Okay, so this dot is not just a multiplication operator. This is a product, vector product, scalar product between 2 vectors. So this will give you the those projection data information, and this A times I basically will give you A over X. Okay, and similar. So basically, this will be your final result. So we know that the X direction resultant force component will be just equal to integration of this over P on all the X projection of the surface. Okay, AX or all the X. And similarly for the Y component, you get this. You can use this equation here, and Z component for you can use this equation. So this makes our problem much simpler here for this curved case. Okay, so basically is that instead we are doing it in a vector way, we just doing that in component way, like on both X, Y, Z, they can be handled independently. We handling X first using this correlation, and P and the integration. So make this is just like a flat plate problem, on the X one, and make this is a flat plate problem on the Y one, and flat plate problem on the Z one. So by doing this way, we make this curved surface, will become this curved plate cases will be similar to those equation we derived for the flat plated cases. Those equations we derived for the flat plated cases can be also be used for each individual one here, because for each one they are really handling. This one is really like a flat plate on Z direction, flat plate on Y direction, flat plate on X direction. So we do this decomposition form. Okay, and so I will stop here, and the next class we will go further with this curved cases, and also do an example problem for it, and we'll continue. Okay, and 2 things before I finish. You will have a quiz problem for today, to take your to account for your attendance. Okay, so there is a quiz problem here in the quiz folder, so you need to finish it before the 3 p.m. And second thing, I assigned the homework problem for the I assigned the new homework problem today. Okay, and it will be due in 2 weeks. 2 weeks means that, which means that it's October 5th, Monday. And remember that that Friday will be our first midterm exam. Okay, so this homework basically is just the right before the first midterm exam. Okay, and I give all the problem for this chapter 3 problems, but right now because I didn't finish this chapter 3, so I think right now you can only finish the first 4 problems. Okay, and there are total 8 problems altogether. Okay, in the next class, you should be able to finish every, after the next class, you should be able to finish all the problems. Okay, and remember that our first midterm will cover basically the content from chapter 1 to chapter 3. Okay, and that's it.
Professor?
Yes?
I just checked the Wiley Plus homework, the second one, and you just have it, it says that it's due today at 3 p.m.
Oh. Which one? This one? Okay, so maybe a typo. I will change it. Is not this due to, is right? You mean the quiz or mean the homework?
Homework, yeah, homework number 2.
Yeah, it's due on October 5, 11:59.
Well, when you click into it, under the due date tab, it says that it's due today at 3 p.m.
Oh, really? Okay, I will change it. I think it's typo. I will change it right away. Okay. Yeah, give me like 10 minutes after the class. I will change it. I'll fix it.
Okay, thank you.
Yeah, and also do not forget this quiz problem. Okay. All right. So, if there is any question, you can ask me now. If there is no question, I will try to see you Friday. Okay. And on the Friday, I will also give you the details for the midterm. You know how we can handle it. Okay. All right. No question? Okay, so I will just close this Zoom here. I'll see you on Friday, everyone. Bye.
Bye, Professor.